Thanks everyone for coming to today's session. It's sequencing DNA with David Eccles. Please welcome.
DNA. It's in our blood. It's in our food. It's even in our genes. DNA is in the air that we breathe, and in the dust and dirt that we sweep into the rubbish bin. DNA is the recipe book of the living world and is present in almost everything that's living or dead. Tēnā koutou I tēnei ata. Ko kurahaupo te waka. Ko tapuai o uanuku te maunga. Ko wairo te awa. Ko rangatane te iwi. Ko huataki taku tipuna. Ko moa taku whānau. Ko rawiri ekuru tōku ingoa. A couple of weeks ago, I extracted some DNA. Now, this thing that I extracted wasn't just DNA. There was other salts and proteins that decided to tag along for the ride. But I had DNA. It was here. I could hold it. And I was curious to know more. Consider a model of DNA. Now, this model may tell you that DNA is a double helix, two coils twisted around each other. The model may also tell you that DNA is composed of 4 basic building blocks, 4 different letters for 4 basic building blocks. The process of converting from the physical object to the sequence is called DNA sequencing. DNA sequencing was used to study the epidemic of the Ebola virus in remote parts of Africa. DNA sequencing was used to determine if a new case was a new outbreak or a continuation of something that had happened previously. DNA sequencing has also been used on the slopes of a volcano in the rainforest of Tanzania. In this case, researchers were trying to work out the diversity of a tree frog and were able to sequence DNA only a few meters from the frog's natural habitat. These two things that I've showed you, these are only possible because of a new idea, a new sequencer that's been developed. A small sequencer, the size of a muesli bar. This is the Oxford Nanopore MinION. This is a sequencer that's so small that it can be taken almost anywhere. A sequencer so small that it can fit in the grooves of the shipping crates that transport the other sequencers of today. Now, the process of this sequencing that is done by this device exploits the electrical properties of DNA. You have 2 fluid-filled channels which are separated by a barrier. DNA is penned in to the input channel, but is encouraged to move to the output channel by the application of a very mild electric current. Now, the only way that DNA can move through that barrier is through very, very tiny holes that are embedded in the barrier. Attached to these holes are very, very sensitive sensors that detect changes in the DNA as it moves through the pore. I call this sequencing by observation. Now, a couple of weeks ago, I was quite anxious as to whether or not this device would perform for you on the day. So, as anyone would do, I baked something earlier. What you're seeing here is the very start of a sequencing run. In this run, at the start, the computer is trying to determine which of those sensors are working, which sensors are connecting to things that have all the necessary components required for getting DNA sequencing done. On this device, there are 512 of these electrical sensors, and each sensor is connected to 4 different wells. So this process takes a while. It takes about 10 minutes. But what I want to show you is something that I've been working on just now. Can we have that on screen now? At the top of the display here, you can see little squiggly lines going along the screen. Each of these squiggly lines represents a single one of those 512 sensors. Now, when the laptop has detected a full DNA sequence moving through the pore, that sequence is collected up into a model affectionately known as a squiggle, then written to a file and dumped on the computer. At the same time, this sequence appears as an additional data point in the bar plot below. Now, this squiggle isn't particularly useful for people to work with at the moment. We don't have the tools available to work with it. But Oxford Nanopore, who designed this device, have come up with a useful stopgap measure. This model is uploaded into the nebulous internet, where it's converted into a standard DNA sequence. This sequence is then downloaded onto the computer, where it can be processed and analyzed using standard sequencing tools. Now, what you're seeing now is the very, very start of a sequencing run. What it does at the start is try and calibrate things to work out whether or not things are working. But give it about 30 seconds and you start seeing sequences. Here we go. There we go. There's our first sequence. It's working. So you'll see here, it's only been running for 30 seconds, and we already have 30 sequences that have come through the sequencer. Each one of these sequences will be being uploaded and then downloaded. Now, I'm not sure whether or not things will have had time to download because it's only been 30 seconds, but I might as well check. Okay, we have here my 3 backup sequences that I generated yesterday. I'm going to show you what you might do with that downloaded sequence once it's been produced. One thing that we can use is a web-based tool called BLAST. Now what I'm going to do is I'm going to open up one of those sequences that I've downloaded and find the DNA sequence that has been created. It's in here somewhere. Bear with me. There we go. Now I'm going to use this web-based tool to try and work out where this sequence came from. This is a program called BLAST, and it searches your DNA sequence, compares it to a public database. We have a match. Let's see what it is. Solanum lycopersicum. Tomato. That's good, because 2 weeks ago, tomato was the thing that I extracted in my home. Tomato was the thing that I purified in the lab. And tomato was the thing that I loaded onto the sequencer and started sequencing. Indeed, the DNA fragments on the sequencer have a tomato sauce. I want you to have a think about what this might mean. I can take a food item from my pantry, run it on a DNA sequencer, and very quickly work out where it came from. Consider a future, a few years from now, where you go to a doctor's surgery. You go in, maybe with a cold. A nurse comes in, takes a swab, and you sit down and wait for the doctor. By the time the doctor is ready for her consultation, your DNA sequence could be ready to go on the DNA sequencer. By the time the doctor is finished, she will have had enough data from the sequencer to determine whether or not that cold was a bacteria or a virus, and possibly give you an idea of what you might expect to happen over the next couple of weeks. I like to think outside the box. When I see wavy, squiggly things, I think of sound waves. What if we could listen to DNA? "17 seconds, about 1,061 base pairs. What you just heard was tomato DNA moving through a nanopore. But what about cost? For the price of a ticket to Cambridge in Great Britain, you could buy one of these devices and still have money left over for a few small sequencing runs. In a couple of years, the cost of sequencing runs would be reduced to about the price of a trip to Cambridge here in Hamilton in New Zealand. But the greatest cost, the thing the sequencer most needs, is trust and time. Researchers need to trust in the potential of this disruptive technology and find new methods and tools for developing it. People need to trust the researchers and get interested and excited and help create the future. With enough people getting excited about this, researchers wouldn't need to fight for trust. They wouldn't need to justify time spent on researching this technology. The researchers would then have the mandate to shift this technology from out of the lab into the field, the doctor's clinic, the workplace, your workplace, and our homes. These interested, excited people are the ones who like to see ideas spread and grow. These people are people just like you. Thank you.